Assalamu alaikum. Welcome to lecture 26 of natural language processing. This is actually the last lecture of this semester for natural language processing. So today we will be discussing contextual embedding and transfer learning, which is chapter 11 of your textbook. Most of the stuff in this chapter is slight differences from the previous chapter on transformers. So we will be able to cover this in a relative uh, uh, in a short time. So in the original plan for the course, we did have some other topics like summarization and question answering. I will just mention a few words about those topics, and we won't be able to start those topics in detail because we're already out of time. So I think that's basically the agenda for today. So let's then get started. All right. Are there any questions? So, so we are going to discuss the bidirectional transformer. So previously we had discussed the transformer which we call the causal or backward-looking transformer. In the causal transformer, the transformer was only able to look into the context that was preceding the current word or the current token that we were interested in. So whenever you have a sequence, we were only relating a particular word at a particular point in time with all the words in the preceding sequence. So that was known as the causal or the backward looking transformer. The bidirectional transformer is actually able to look at the context on both sides of a given position. So if you are at a particular position, let's say at a particular word, it can look at or it can relate to words preceding that word as well as can relate to words after that word. And this has it has advantages in many applications because in NLP, oftentimes we know more about a word if we are able to glean information from the following words, not just the preceding words. So the traditional language model only looked at the preceding words, but it can benefit from looking at the next word as well. Other examples could be, for example, let's say if you have a problem of, for example, named entity recognition. So, and also in POS tagging, many other applications. So if you have a name like, so for example, you can think of the word Teddy. So Teddy could be the name of a person. It could be something else as well. For example, it could be teddy bear as well, which is not a name of a person. So, but if Teddy appears in a sentence and you have some information that appears after Teddy that tells us that Teddy is actually the name of a person, then NER would benefit from this. So, but this benefit would not be useful if you're using a causal model. So, for example, Teddy went to school. So obviously a bear would not go to school. So this sequence of words after this Teddy tells us that Teddy is most likely a person. So we can benefit from information that comes after a particular position. So this is exploited or utilized in the bidirectional encoder. So the most popular bidirectional encoder is what is known as the BERT, B-R-T, B-E-R-T. So actually, many of the names of modern models in NLP are based on some famous children characters, BERT or Elmo and so on, Robota. So BERT, by the way, stands for bidirectional encoder representation with transformers or using transformers. So this was proposed around 2019. So it's a recent model. And since then, it has become one of the main models for processing NLP. It has become very popular. And it does gives better results than traditional NLP. Of course, one of the reasons for that is transfer learning, which we are going to talk about also today. All right, so let's discuss what BERT is. So we have already discussed the transformer, the standard backward-looking transformer, and we know that it has the notion or a mechanism which is called a self-attention. So the bidirectional encoder also has this self-attention, but this self-attention now is not just focused on the preceding words, it also considers the next word. And it turns out that actually there isn't much of a difference. The equations that we studied earlier for the causal transformer are the same for the same equations that we will study or that are used in the bidirectional encoder. So let's quickly review that. So I will write the matrix formulation of it. So we know that we can generate a query matrix for all the words in the sequence by multiplying X, which is all the words that are inputted. So usually in transformer, we input a fixed sequence of words. If the actual sequence of words is longer than that fixed, you will truncate it. If it is shorter, we add some padding in it. So this is X. X is, of course, size T by D. D is the embedding size. T is the length of the sequence. So we multiply this with W, Q. Q, of course, is a superscript, it's not a power. So this is a query representation or role for each of the word in the sequence. And then we have the key role, which is X into the matrix multiplication Q or WK. And then we have the value role. This is X into WV. And as we mentioned last time, this WV, WQ, WK, the output dimension may be different from the input dimension. The input dimension, of course, is D, which is embedding length. The output dimension may be different, which we can say is DK. So D subscript K. And similarly, the output dimension for V, the value vector, may also be different, and we denote with DV, subscript V. But of course, you can keep it same as the input embedding size as well. So these are the various rules. And then after that, we used to compute the self-attention. And this expression actually combines multiple operations, softmax of Q, K, transpose. This is transpose, divided by, of course, normalization SQRT with DK, let's say. So this was the equation that we talked about when we discussed the self-attention previously. And this equation still holds for the bidirectional. The only difference that we will have is, if you remember this matrix that we computed, let's say I call this matrix A. This matrix, of course, is size T by T. A is matrix size T by T. T is the sequence length. So this is a T by T matrix. So previously we had masked the upper diagonal of this matrix. Masked meant that we added a very small value, minus infinity, in those cells, meaning that those cells do not contribute to the relatedness information. So the upper triangle actually had information for the subsequent words given the current context word, the current word. So we masked that, and that was required if you wanted to do the traditional language modeling, because in the traditional language modeling, you're predicting the next word given the preceding word. So if you did not mask the next word was already present in this matrix A. So that would be trivial. So we had to mask it because we wanted to predict it, not to actually look it up from the matrix. So we masked it. But now, since we are doing bidirectional encoder, we will not mask the upper triangle. So that is the only difference. So basically no masking of the matrix A. Okay? So which means that if you have a, let's see, so the matrix would be a full matrix, as I said. It will be a full matrix. And of course, the current word would be represented by the diagonal. And when you take the softmax for any row, you will take the softmax over all the words in that row, except, of course, including the diagonal as well. Previously, we were only taking the softmax for all the words up till the diagonal. So previously, we are only taking the softmax until the diagonal. Now we are going to take the softmax for all the words for the entire matrix, for entire row of the matrix. And this softmax would give you the scalars, alphas, which are the self-attention weights. And those weights are then used to produce the output. So the output, as we had discussed previously, AI is basically equal to, you have a summation over all j of alpha ij into vj. Previously, this j was less than equal to I. Now there is no such restriction. Okay? So in other words, the output at any particular position is based on, you can say, self-attention from all other words in the context, in the sentence, in the passage that is inputted, including the preceding words as well as the following words. So this is essentially the bidirectional encoder. The rest of the model is essentially the same as we discussed before. You may have multiple heads. All of those heads would be in parallel. The output of those heads may be concatenated, then fed through some feed-forward layers. And then you may have some, additional feed-forward layers with layer normalization, with skip connections and so on. And then you may have the output layer. Output layer would depend on the task that you're working on. So if you're doing classification, then output layer would have k nodes corresponding to the k classes. So the rest of the model essentially remains the same. And actually all equations essentially remain the same, only that we do not do masking. So this is, as I said, the bidirectional encoder model. Now the question is, how do you train this model? So remember, we trained the causal model using language modeling, which was predicting the next word. In this case, you cannot predict the next word, obviously, because you already have that next word in our model. It's simply look up. We want it to be learned. We want to train it. So looking up would not cause any training. So we have to then modify the training mechanism. So that's the main contribution, I would say, of BERT. the idea of bidirectional itself is not a big contribution. The training was the main contribution. So let's discuss that. So they introduced two training losses, you can say, or training scenarios, which they actually trained together. So let's first discuss each of those scenarios separately. The first one is what they call the masked language or MLM. And the next one, the other task or you can say loss that they tried to minimize for training was the next sentence prediction. So let's talk about the masked language model, MLM. So again, you cannot use the standard language modeling, because in the standard language modeling, we are predicting the next word given the given the preceding words. Here, the next word is already in our model. We cannot use it. So we have to modify the language modeling scenario. So what they do is they use the notion of the concept of filling in blanks. Fill in blanks. So remember, you might have a sentence. So I dash 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 in Lahore. So there's a blank there. So this blank is the word that needs to be predicted based on the context that precedes that blank as well as the context that follows that blank. So now this, if you are able to do this, now this model would be bidirectional for language modeling as well. So we can predict the blank or missing word based on the words that come before it as well as the words that come after it. And we can use the bidirectional encoder because you have information coming from both sides. So this is what it essentially does. And of course, to do this in a more robust way, it proposes a specific approach. So obviously, since this is language modeling, we can use any corpus that is available for a given language, as long as that corpus is correct for that language, meaning that is written properly. And we don't need any external labels. The labels are already present in the corpus, just like for standard language modeling. So given that, then we basically then randomly select 15% tokens for filling in. In other words, we randomly select 15% tokens in our entire corpus, and we say that these are the blank tokens. These are the tokens that we would like to predict. Okay? So from these 15, we have a further categorization. And this is required because we want the model to learn all the scenarios. So 80% of this 15% are set with a MASK token. So this is a fixed token that you specify, and this token basically identifies it to be a mask. ठीक है, कोई भी आप एक random fixed token fix कर सकते हैं and then use it for this. So then 10% of the 15% that you have selected are set to a randomly chosen token in the corpus, of course. So some other token. Okay? And then the remaining 10% is set to the actual token. So whatever you have selected for filling in, you use that. Only 10% of those. So 10% are some other word, And then, of course, 80% are masked, meaning that you use that mask token for it. So let's just take a quick example. So I went to eat at, let's say, McDonald's, MD. Okay? So let's say this is the complete sentence. And of course, this is a very small sentence. So 15% randomly आपने words select करने हैं. So let's say eat is selected. So this is the blank that we are now considering. So in this particular sentence, let's say there was just one blank that was selected. So यहाँ obviously पहले eat था. So now again we do another random number generation, and 80% of the time we change this with the mask token. Okay, 80% of the time. Of course, this is all done randomly, so it will be done mask if mask is selected, and if any other random word is selected, then so let's say any other random word is selected. Let's say कुछ भी और select हो सकता है. Let's say D select हो गया. So this would be some other random word. So that is the 10% of the case. And the 10% of the case, we leave it as eat. Okay? So any given word with any given blank would be either be masked, it would either be some other random word, which is of course incorrect, and or it could be the actual word itself. In other words, you can say that we had not masked that word. Okay? And of course, usually we will be giving up to 5. By the way, BERT as well as many transformers are based on subword tokenization. And they typically use the word piece tokenization approach. So in other words, we will be masking subwords, not complete words. Whatever that token is, it can be a subword. And as I said, you can take up to 512 subwords in the standard BERT or transformer. So within that 512 sequence of words or subwords, you may have multiple blanks because you're taking 15% of it randomly. And then, of course, those multiple blanks would be filled in by mask or the actual word or some other word. Okay? So this is how you prepare the data. Now, how do you actually, what is the loss? So we actually predict the, or you can say, output the Y for all you can say blank positions. So those 15% that you have selected, you generate the output Y for those positions. Remember, output Y goes from A to an output layer Y, which is Y is a softmax over the entire vocabulary. ठीक है? So उस जो 15% वर्ड्स हमने सेलेक्ट किए थे पहले, उनका Y हम निकालेंगे और वो देखेंगे कि is it the correct missing word or not. So that output Y could be from a mask or could be from actual word or could be from a other error word. Okay? But of course, the loss at the end of the day should be the actual word. ठीक है? तो ये loss हम basically minimize करते हैं in BERT. Not for all words, only for those 15% words that are chosen to be filled in or those 15% words that were selected to be blank. Okay? And actually, this is one reason why training BERT is somewhat slower than training a standard language model, because we are not working on all the tokens. We are only working on 15% of the tokens. Of course, when I say slower, I would say slower when we are comparing two models of the same size. So we have a causal transformer and a bidirectional transformer of the same size. The bidirectional transformer, when trained on the MLM, would train much more slowly because we are updating only 15% of the words in the random process. While in the standard causal transformer for language modeling, we'll be using all tokens and updating them. So this Y, as I said, is a softmax over the vocabulary. It should be the actual word. So for example, let's say जो ऊपर था मेरे पास, I went to eat. So let's say ये मार्क्स था मेरा at MD. So जो मार्क्स की पोजीशन पे जो आउटपुट Y आया है, it should ideally be eat. If it is not eat, then this is the loss. इसी तरह हर एक के जो भी ब्लैंक या फिल्ड इन पोजीशंस थी उनके लिए हम लॉस निकालेंगे और फिर एग्रीगेट करके स्टोकेस्टिक ग्रेडियंट डिसेंट से अपना नेटवर्क अपडेट करेंगे. ठीक है, so this is the Max language model approach. But the BERT people actually use two losses together. The second approach was the next sentence prediction. So the next sentence prediction, as the name suggests, here we are trying to predict the next sentence given the current sentence. And this also basically captures, you can say, semantics and syntax of a particular language, just like language modeling captures semantics and syntax of a given language. So this, of course, is important. Let's say if you want to determine coherence, for example. So if two sentences are together in a given passage, of course, that means that that passage is coherent. But if they are taken from different positions of a passage, then it means that those two word sentences do not represent coherent language. So coherence, of course, entailment is another application. Entailment essentially means that if you are given two sentences, we can say that the second sentence is entailed from the first sentence, meaning that it is derived from the first sentence, or the meaning of the second sentence can be derived directly from the first sentence. So that would be entailing. And of course, if it is not derivable from the first sentence, that means that does not entail. इस तरह की application में भी ये relevant है. Of course, इसमें question answering भी आ जाएगा. First sentence would be question, second would be an answer, which again is a special form of entailment. ठीक है ना? तो second answer is actually, you can say, second special form of predicting the next sentence, and so on. So you can have various applications. But the bottom line here that I'm trying to express is this is also capturing syntax and semantics of the language. And the whole idea is we want to learn that from the data. So in this case, what is our training data? So 50%. So we basically take sentence pairs. So sentence pairs. So 50% are actual pairs from the corpus, meaning that they do follow one after the other. And the remaining 50% are random, meaning that if you have the first sentence, the second sentence is randomly selected from some other position. So they are not exactly following the first sentence. So this is our training data. And since this is next sentence prediction, it's a classification problem. We shape our data in this way. We have a CLS token at the start. We have first sentence tokens. And then we have a SEP token and the second sentence. Okay. I mentioned this last time as well when we were discussing transformer for classification, let's say for paraphrase detection. So you can have a SEP token between the two paraphrases, and you have a CLS token that captures the classification of that particular problem. Okay. So in this case, of course, this is net sentence prediction. We put the two sentences together with the set between them, and there is a CLS token. So the output of the CLS token, which is A1 in this case, the first token, A1 would be developed by looking at all the words in the sequence that follows it. Okay? Remember, this is bidirectional. So this CLS token A would contain all information of both sentences. And then, of course, you can then build a classifier after this token, meaning that you can get a YI after this, Y1 after this. And that Y1, in this case, would be binary classification. Okay? Done on CLS token. And this binary classification would tell us whether the two sentences are coherent, or it's whether the second sentence is actually the next sentence after the first sentence. So, of course, here we'll use a softmax, or you can even use a simple sigmoid as the output layer, and you can train the model using the cross entropy. Okay? So this is the second task that BERT uses. The first task was MLM, mass language model, and the second is the next sentence prediction. And actually it does it together. How does it together? तो ये sentences उसी तरह ही लेता है जैसे आप मैंने बताया कि 50% sentences were two sentences together in the corpus and 50% were not. So within these two sentences फिर उसमें से 15% mask कर लेगा. So masking भी उसमें हो रही है, next sentence prediction भी हो रही है. Remember, next sentence prediction loss होगा CLS का, CLS के आउटपुट पे, और मास्किंग का लॉस वहां से आएगा जहां आपने मास्क किया हुआ, जहां आपने सेलेक्ट किया रैंडम टोकन फॉर फिलिंग इन. सो बोथ लॉसेस को वो एग्रीगेट कर लेता है वेटेड फैशन में, वो डिटेल वी वोंट गो इनटू, एंड देन डज द बैक प्रोपगेशन फॉर अपडेटिंग द नेटवर्क टुगेदर. So both MLM and NSP losses are aggregated and then used for updating the network. Okay. So this essentially is the BERT, the bidirectional representation with transformers, which was proposed in 2019. And this model, as we discussed, is trained on large amounts of data for a given language. So if you're talking about English, we'll collect millions and billions of words for that language, and then construct the training data in this way, maybe 50% pairs of sentences, 50% non-pairs of sentences, and within those pairs, 15% are masked, then do the MLM and NSP losses and update the network. So once the network is trained, so it would have learned, as I said, a lot about that language, syntax, semantics, discourse, and so on. Because we have given it lots of data, and we have used the context from both preceding and next positions for language modeling, and we have also modeled whole sentences and whether those whole sentences follow one another or not, meaning that coherence of language. So it would have learned a lot of stuff. So now actually you can use this model in many downstream applications, not just for language model. So that's where we come into the transfer learning thing. So we have, as I said before last time as well, so transfer learning is whenever you learn on one data, that knowledge can then be used to improve the performance of some other task or on some other data. So that's transfer learning. So we have already trained BERT, and now we can use it to solve many other problems. So first of all, actually, there are two things that we need to discuss. So there's transfer learning, and the other thing is contextual embeddings. So previously, we had talked about word-to-vec, which was static embeddings. So static embedding means that for any given word, you have one embedding, irrespective of whether that word appears in one context or another context, meaning that that word could appear in different cases. For example, I usually give the example of live and live. So I live in Lahore. So LIVE is a word, and I watched the match live. So again, LIVE. But if we had used word-to-vec, LIVE would have just one embedding, unless you had done some other tweaking. It would have just one embedding, and it would be fixed. Whenever you are processing the first sentence, I live in Lahore, we'll use that embedding. Whenever we are processing the second sentence, I watched the match, that we will use the same embedding. But as you can see, because of the context, the second context is about match, and LIV here is actually an adjective. While in the first case, I live is actually a verb, and it has a different meaning. So what you can do is, let's say you have a trained BERT model. If you feed in these two sentences, if you feed in the first sentence, I live in Lahore, अब जो live का जो output है A, so that can now be considered as a contextual embedding of live. Okay? So it would depend on both the words that precede it and the words that follow that particular word. So that's why we call it contextual embedding. And this embedding would be different from the embedding that we get when we feed the second sentence, I watched a match live. अब यह live इसमें आप घुसेगा इस BERT में, उसका जो output होगा A, that would be different from the output that we got from the first sentence live or live. So we can use this vector A that is obtained by passing a sentence through BERT as the contextual embedding, embedding that is based on all the words that appear around that particular word in a sentence. So this embedding would be more expressive than the word-to-vec embedding that we talked about earlier. So is this point clear, the contextual embedding? So once you have a trained model, you can feed any sentence for that language into that model, and for each word of that sentence, you will get an embedding. The A's that you get are the embeddings. And those embeddings, as I said, are contextual. They are not fixed. They depend on the actual sentence that you fed into the network. And then you can go ahead and use these embeddings in any downstream application. Again, this is transfer learning. Why? Because we have learned these embeddings from some corpus and then use those embeddings elsewhere. But another important way of using transfer learning, especially in this case of BERT, is through fine-tuning. So we don't use any new model, we just use the original BERT model and fine-tune it. So in this case, so you have the bidirectional encoder model, which has been pre-trained. So there is a pre-training, which is of course BERT. Pre-trained, of course, using MLM and NSP on a given language. So this has already captured all of the information. Now let's say you want to use this model for, let's say, sentiment classification. Okay? So this is a classification problem. So what would you do? Instead of just getting the embeddings for a given sentence, so I like the movie, एक तरीका तो ये हो सकता है आई लाइक द मूवी आप फीड इन करें और आई की एम्बेडिंग ले लें, लाइक की ले लें, दी की ले लें और मूवी की ले लें, ये एम्बेडिंग्स आ गए. अब ये एम्बेडिंग्स लेके आप एक सेपरेट नेटवर्क ट्रेन कर लें a feed-forward network or a recurrent network to do the classification. But why would we like to do that? Why can't we just use this? So we can use just this same model. जो BERT model है उसके आगे ही हम further उसकी classification कर ले रहे. So in other words, we have a CLS token. So I like the movie. ठीक है, ये हमने फीड इन किया और जो CLS टोकन है इसको हमने हमारे जो ट्रेनिंग डेटा सेट था सेंटिमेंट क्लासिफिकेशन के लिए उसके लिए फाइन ट्यून कर लिया, मीनिंग दैट उसके ऊपर हमने फर्दर ट्रेन कर लिया. एक तो प्री ट्रेनिंग होगी थी जो हमको मिल गई फ्रॉम सम थर्ड पार्टी. नाउ वी वांट टू सॉल्व ए क्लासिफिकेशन प्रॉब्लम. हमने उसको इस तरह का डेटा दिया, फिर उसको हमने फर्दर ट्रेन कर लिया यूजिंग आवर बाइनरी, लेट्स से cross entropy. Let's say we are doing just positive negative classification and updating the CLS token, and of course this will update the network. So this is process is called fine tuning. वही network हम use करें, वही सारा network parameter use करें, simply जो उसके output layer है वो हमने पुरानी वाली हटा दी. पुरानी वाली में of course क्या था, हमारे पास MLM था और NSP था. NSP था for CLS. वो हटा के अपनी एक क्लासिफिकेशन की लेयर डाल दी, सेंटिमेंट क्लासिफिकेशन, अपनी सेंटिमेंट क्लासिफिकेशन का डेटा उसके ऊपर ट्रेन कर दिया. सो दिस इज कॉल्ड फाइन ट्यूनिंग. एंड सिंस वी आर रीयूजिंग ऑल ऑफ द इंफॉर्मेशन फ्रॉम the pre-training, this often is quite fast, quite quick, and it's also very accurate, but lots of information is carried forward. ठीक है. So this step is then basically called fine tuning. Okay, so we have a pre-training, which is the BERT model that has been trained by a third person. So trained models are already available on large amounts of corpus. You just take that model, and then you have your own small sentiment classification label data set. You use that model and update the model on the CLS token. And of course, it will update the entire model because CLS is attached to all the other tokens through the self-attention. Okay? And then, of course, once this model has been trained, then you can use it for sentiment classification. And yet you can do this for anything. So all classification problems. So let's say you have a topic classification problem. So you can think of, let's say, emails classification, and so on. And it can also be used for sequence labeling tasks. So sequence classification, sequence labeling. So sequence labeling would be like POS tagging, NER. Okay. So in this case now, for each output, each token, you update the output layer and you have the appropriate output layer. Let's say if you're doing POS tagging, the output layer would be a softmax over the all possible POS, and you would use your own POS training data set to fine tune the network. And similarly for NER. Okay, so are there any questions so far? All right, so I think that covers essentially most of the stuff that I wanted to cover. Just a few comments on transformers. So transformers have become extremely popular, and they're also quite useful, as many applications have demonstrated in the past 3-4 years. And lots of transformers have been proposed, uh, and they have been pre-trained on lots of data, and with various tweaks as well. So what I often call this as the transformer wars of recent years. So lots of transformer models have been proposed. Of course, BERT is a transformer. Okay. So BERT, of course, is just a single model. You can say it's an encoder-based model. Okay. Uh, it's basically a transformer, a single transformer. Uh, and then, of course, people have developed other variations on BERT. So, for example, there's a BERT called Roberta. So this is robust BERT or robust BERT, adaptive, and so on. So it has some tweaks in it. So there are also smaller versions of it. For example, distill BERT. So distill BERT is a distilled version of BERT, which is of smaller size and can often be trained on, you can say, um, on data sets much more quickly. And then, of course, there are many others. So also there are multilingual models as well. So for example, MBERT is a multilingual model. So and these models have been trained on hundreds of languages, and many of them have been trained on Urdu as well. So there is MBERT and there's also M Roberta and I think XLM Roberta. But okay, Roberta का एक और variant भी है X extra, I don't know what that stands for, XLM multilingual Roberta. ठीक है? And of course, as I said, there are many variations, and those variations would be variations in the data set that has been used to train the models, in the number of parameters in the model, whether the model is big or small, how many layers do you have, how many multi-attention heads do you have, and then, of course, many other tweaks like whether they're using distillations or whether they're using multilingual and so on. So all of these tweaks have been done, and these models are already available. And then there are also other models, for example, GPT, you might have heard about it, generalized pre-trained transformer. And we have GPT-2, which is, I think, freely available. GPT-3 is a bigger one, which is, I think, recently has been made freely available. But this is a massive model. But these models are both encoder and decoder. So in other words, they have two transformers, one transform for the encoder, one transform for the decoder. So these models generally do better when you are doing sentence generation task, as opposed to BERT, which can be used for sentence generation, but they are primarily trained for prediction. So they work well for prediction tasks like sequence labeling or sequence classification. But if you want to do, let's say, paraphrase generation or summarization, these encoder-decoder transformer models are much better. And of course, these are also trained on appropriate loss functions that are appropriate for generation. So GPT is an example of that. And then there's also a model from Google, which is called T5, which stands for, I think, text-to-text transformer, transfer transformer, I don't know. So that 5 T's there. And there's also a multilingual version of this, MT5, which is actually quite useful for Urdu as well, because it has been trained on Urdu. And then, of course, there are other more recent models. If you just do a simple Google search on recent transformer model, you'll find some other names as well from Microsoft, from Google, which are variations or extensions of these models. And these models typically are huge, massive. They have millions and billions and trillions of parameters. So the good thing of being massive, of course, is that they contain a lot of information, and they learn a lot about the language, and you can simply fine-tune them for your particular task. The bad thing sometimes arises is because they also learn something that are undesirable from the data. So things like hate speech, things like biases, gender biases, and so on. So we talked about this earlier on as well, and this still applies to these models. All right. So regarding summarization and chatbots or question answering, most modern, of course, if I had discussed these two topics in more detail, I've done it in more systematic way. But as I said at the start, I'll just give you a few words about this. So modern summarization techniques as well as question answering techniques are all based on transformers. Okay? So in essence, really, you don't really need to study the theory of summarization or the theory of question answering or chatbots. Uh, as long as you have training data, just feed the training data to these transformers and they will be able to learn the mapping from the input to the output. Of course, those theory would help you in some extent to fine tune or make your model better. But as I said, we don't have time to do that now. We have run out of time in this semester. So for example, so let's say question answering. So how would question answering would be done? So in the standard case, you have basically CLS, you have the question word, you have subtoken, and then you have the answer. So you need data in this form. And you can use the BERT type of model. Of course, since remember question answering is also like generation, you are generating the answer. So sometimes you can use BERT, of course, but usually the encoder decoder model usually would work better like GPT and T5. Okay. So the bottom line in this case, of course, you need to have those pairs, questions and answers, questions and answers. If you have lots of them, you train the model, which are already pre-trained, and fine-tune on this, you will be able to do a very good job. So similarly for chatbots. So chatbots, of course, is a sequence of questions and answers or a conversation between two people or two agents. So here again, so you have a CLS token here, and then you have, let's say, the first person, the SCP, and the second person. So first person statement, the second person statement, and you can continue. Of course, if you want to return, keep the history, you can update this model by retaining some history. Remember in chatbot you have a history. So previously कुछ बात की हुई है वो बाद में फिर reuse हो सकती है. तो उसके लिए models update कर सकते हैं, and people have proposed many such variations. You can do that, but the core still remains a transformer or a transformer as encoder and transformer as a decoder. Okay. There is another type of question answering which is called comprehension. So which is, I think, for those who have done A level, O level, even metric, FSC. So you have comprehension problems in English, right? So what is the comprehension? So you are given a passage, Uh, so given a passage and then answer questions based on the passage, right? So in your exams, you are given a article, let's say, and after that you have 4 or 5 questions from which you need to answer, give from the passage. So you can also train a neural network, a transformer to do this as well. Kis tarah? So usually, so the training data would be something like this. You have the passage, and in that passage, you basically identify the span that contains the answer to a particular question. So let's say, so आपके पास एक्चुअल क्या होगा, CLS टोकन डाल दें, और इसका इतना यूजफुल नहीं है, फिर आपके पास सेप है, उसके बाद क्वेश्चन है. ठीक है, इस तरह आपका इनपुट बनेगा. You have a passage, and you have the question. Question, of course, is sequence of words. Passage is sequence of words. ठीक है? अब इसमें जो हमारे पास जो आउटपुट होगी वो उस पैसेज में हम एक स्पैन आइडेंटिफाई कर लेंगे जो उस क्वेश्चन का आंसर वहां मिल रहा है. सो स्पैन क्या होगा? सो बेसिकली आइडेंटिफाई और डिटेक्ट span in passage that answers the question. ठीक है? Span is what you have a start label, and then you have an end label. Of course, you can even have start, end, multiple. That will be more complex. But simplest case is contiguous. एक start position है, एक end position है, उसके दरमियान वो answer उस question का आ रहा है. ठीक है? So for example, let's say you have a long passage, da 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 da. So he was born in Lahore. Then you have a long passage. Or let's say आपके पास SEP question था, when was let's say Asif born? ये question है. ठीक है? तो अब इसका answer is lies in this passage. So ये तीन words हम इन वर्ड्स की जो आउटपुट होगी, इनका जो एज होगा, इनका जो वाई होगा, जो बॉर्न का वाई होगा, दिस विल टेल अस के दिस इज द स्टार्ट ऑफ द आंसर टू दिस क्वेश्चन. इनका जो वाई होगा, दिस वुड से दैट दिस इज, बाय द वे, BIO इंकोडिंग भी कर सकते हैं आप, जो हम NER में हमने डिस्कस की थी. सो स्टार्ट, इनसाइड एंड आउटसाइड. ठीक है? सो स्टार्ट यहाँ होगा, इनसाइड होगा, और लाहौर भी इनसाइड होगा, एंड देन दैट्स इट. So this whole passage would be an answer to this. So you can solve comprehension problems, and you can train a pre-trained, or you can fine-tune a pre-trained encoder-decoder model to solve comprehension problems. And they are pretty accurate, especially if you use large amounts of pre-trained data for pre-training your models. Okay? So this is solving comprehension problems. And of course, you can also solve fill in the blanks problem, which are also common in many of your exams. And this would be a direct application of the MLM model in BERT. आपके पास कोई पैसेज दिया हुआ है, बीच में एक वर्ड मिसिंग है, तो you can use your MLM model to predict the best word for that missing position. और let's say आपके पास ऑप्शंस दिए हुए A, B, C, D, तो वो उस ऑप्शन से भी वो चेक कर सकता है कौन सा बेस्ट आंसर है. So modern day NLP is heavily dependent on these sequence models, and they are also heavily dependent on training data. If you have lots of training data, essentially you can solve almost any problem. So I think that brings us to the conclusion of this lecture, as well as to the conclusion of new content in this semester. So we had covered essentially the textbook from chapter 1 to chapter 11. So we had focused on basic concepts from text preprocessing to the more modern techniques based on neural networks. And we have also touched upon many applications, and most of those applications can be solved using the neural network-based approaches. You don't need any linguistic or rule-based approaches for that. So we had not touched upon parsing much in this course, which is a reasonably big section of NLP. But one of the reasons for not touching upon that is that in recent years, parsing has become less relevant. we typically focus on the end goal. Usually parsing is not the end goal. Parsing is an intermediate goal to a particular end goal. So since neural networks can solve the end goal directly, so people don't worry about parsing too much. But parsing may have applications where you are more interested in understanding and interpretation of text. So there, of course, parsing would be more helpful. But if you are more focused on, and you can build a end-to-end system where you have an end goal, then you can directly use a neural network to solve that problem. And parsing explicitly is not required. It might be done implicitly through the learning process, but it's not required explicitly. So essentially that's it. So thank you for participating in this semester on in this course on NLP. And now we have our exams, I think, in a couple of weeks after the Eid break. So, so if you like, we can have 1 or 2 sessions of review next week. But I would like to hear from you. If you are interested, then we can schedule that. Otherwise, I will be skipping those. All right, then if there are no questions, we can stop. So thank you for attending and listening.